Welcome. In Unit 1, we studied the structure of a single atom. In Unit 2, we're going to ask the question, what happens when two atoms come together and form bonds? That's what we're going to start to answer today. And it's going to depend upon what types of atoms are bonding. And some of the two useful categorizations we can make here is whether the atom is a metal or a nonmetal. The metals are over here on the left-hand side of the periodic table. Based on our periodic trends, we know they have low ionization energies. They've got a relatively weak hold on their valence electrons. Over here in the upper right-hand corner, we've got the nonmetals. They have high electronegativity values. They've got a strong attraction for valence electrons. So we will form different types of bonds based on the different types of atoms that are going to come together. When we have metals and nonmetals combine, we end up observing a transfer of electrons from one atom to another, and that's referred to as an ionic bond. When you have two or more nonmetals coming together, they will share their electrons, and that's called a covalent bond. And when you have all metals coming together, the electrons are pooled between atoms in something known as the electron C model, which we'll talk about later. And that's referred to as metallic bonding. So you can have ionic bonding, covalent, or metallic bonding. This slide shows a visual of what these different types of bonding will look like. We can see over here on the left, we've got our ionic bonding. When you have ionic bonding, you're combining a metal with a nonmetal. So metals have low ionization energies. They're going to give up their valence electrons relatively easily, and they will form a positive ion. Nonmetals have a highly negative electron affinity. So they've got a high affinity for electrons. They're going to gain an electron and become negative. So the metals will transfer their electrons to the nonmetal, forming a positive and negative ion. And then opposites attract. We know that with Coulomb's law. So that electrostatic attraction is going to hold those ions together, and that is what an ionic bond is just that electrostatic attraction between your positive and negative ions. When you have covalent bonding, this happens when you have two or more nonmetals coming together. Both atoms have high electronegativities, so they have strong attraction for electrons, so neither one of them is really willing to give up their electrons, so the atoms will end up sharing electrons. And then in metallic bonding, you've put together several atoms that all have low ionization energies, weak attraction for their electrons, and those valence electrons move around freely in what we call a sea of electrons. They're kind of not locked in any one location, they're moving around freely. So we're going to dig into some more detail with these bond types. We're going to look at ionic bonding first. We already said ionic bonds form between metals and nonmetals, and here's a review of where you can find those on the periodic table. The metals will lose their electrons. Nonmetals will gain electrons. And again, this makes sense going back to what we know of our periodic trends, because our metals over here tend to have low effective nuclear charges. Their valence electrons are relatively far from the nucleus, perhaps. Down here, they've got a weak grip on their electrons. The nonmetals tend to have a much stronger attraction for electrons because they've got high effective nuclear charge. So if you put together a nonmetal with a metal, the nonmetal will take an electron away from the metal. As a result, you end up with a positive ion and a negative ion, and then electrostatic attraction is going to hold those two ions together. And when it does that, it forms something called a crystal lattice. So those positive and negative ions experience Coulombic attraction, so opposites attract, and they form something called a crystal lattice. And it's really important to be careful with our vocabulary here. There is no such thing as a molecule of salt or any other ionic compound. They don't form molecules. What you have is this big lattice. It's a big, array of, positive, negative ions. So this is a sodium ion, this is a chloride ion, and they just keep repeating in this big pattern. So there is no such thing as like one sodium and one chloride bonded together in a molecule. That does not happen in ionic bonding. They just form this big repeating lattice of ions there. Another important thing to think about with ionic bonding is that the number of electrons gained will always be equal to the number of electrons lost. So the ionic bond is formed by electrons being transferred. And so the number of electrons that your nonmetal gains need to equal the number of electrons lost by your metal. Here's an example of what that might look like in the formation of ionic compound when we combine sodium metal and chlorine gas to make sodium chloride. Your sodium loses one electron, your chloride gains one electron. You end up with a +1 sodium ion, a -1 chloride ion, and that gives you your sodium chloride compound. We'll look at one other example. When we combine magnesium and fluorine, we can write something called a Lewis dot symbol, which we will do more of this with our later topics coming up next, in which each dot represents an electron. And magnesium has 2 valence electrons, so I gave it 2 dots. Fluorine has 7 valence electrons. And we know that our metals tend to lose electrons, our nonmetals tend to gain electrons. So magnesium is going to lose an electron and give it over here to fluorine. Okay, because you see how fluorine's kind of got one opening, so it can accept 1 electron and form a -1 ion. But magnesium has 2 electrons to give, so in order for this to work, we need to have each one magnesium needs to react with 2 fluorines. So what you see is your magnesium will lose 2 electrons, so it forms a +2 ion, and then each fluorine is going to gain 1 electron, so they're going to form -1 ions. When we write the chemical formula for that, we call it MgF2. So the key thing to notice is that, electrons gained is equal to your electrons lost. And the other thing you should notice here, another way to think of it, is the sum of the positive charges is going to be equal to the sum of the negative charges. So notice how we've got 2 positive charges here, we have 2 negative charges. We're also going to take a look at the energetics of ionic bonding. So we said an ionic bond is actually just an electrostatic attraction between the cation and anion, because we know opposite charges attract. And we know that we've got an equation that can describe this attraction. It's called Coulomb's law. And when we're applying Coulomb's law to ionic bonding, we describe the attraction holding these ions together. We call it the lattice energy of an ionic compound. And the technical definition of the lattice energy is it's the energy released when gaseous ions combine to form a crystal lattice. So that's the technical definition of a lattice energy. You can kind of think of it as the bond energy. So it's the energy that's released when these ions come and stick together. And the lattice energy is dependent upon the size of the ions and the charge of the ions. And this might kind of sound familiar to what we talked about with periodic trends. And we talked about the attractive force is proportional to the charge divided by the distance. So as the charge of the ions increases, the attractive force between those ions is going to increase. As the size of the ion increases, that would be like your distance variable on the bottom. So as your size increases, the attractive force is going to decrease. So it's another application of Coulomb's law here, except this time we're talking about the attraction between 2 ions rather than the attraction between an electron and the nucleus. And we can observe this down here in the data. We can see that with the compound lithium fluoride, and lithium fluoride, this is an ionic compound that has lithium has a +1 charge, fluoride has a -1 charge, so it's a +1 -1 attraction. Lattice energy is 1030. If you look over here with MgO, Mg forms a +2 ion, oxygen forms a -2 ion. Notice how the lattice energy is 3700. So both ions here are double in magnitude, and notice how the lattice energy is like almost 4 times as big. Okay, so this shows us an example of if we increase the ion charge, the lattice energy will increase. So again, the strength of the lattice energy varies with the magnitude of the charge and the distance between the charge. When we talked about distance between the charge in periodic trends, we were thinking about the location of the electron within the atom, so like what shell is the electron in. When we're thinking about it in this application with ionic compounds, we're going to be referring to the ionic radius. That is the number that will give us a sense of the distance between the two charged particles. So we're looking at charge magnitude and ionic radius. Okay, so practice problem, lattice energy practice. Who has a higher melting point? So melting point, you might wonder, we haven't talked about melting point yet. Well, how do melting point and lattice energy relate? If a substance has a larger lattice energy, what that means is its ions are more strongly attracted to one another, and it will take more energy to separate out those ions. As a result, we'll end up having a higher melting point or boiling point. So when we ask who has a higher melting point, really what we're asking is which substance has a larger lattice energy. Okay, so let's make some comparisons here. So let's look at sodium chloride versus magnesium oxide. So sodium chloride, sodium forms a +1 ion, chloride forms a -1 ion. Magnesium forms a +2 ion, oxygen forms a -2 ion. So if I make the comparison here, MgO, the ions have larger charges, so they're going to be more attracted, so it's going to have a larger lattice energy. Let's look at this one, lithium fluoride. Lithium is a +1 ion, fluoride has a -1 ion. Sodium will form a +1 ion, and bromide will form a -1 ion. So you might look at this and say, well, they're exactly the same. Now what do I do? Well, remember there's two variables we want to think about. We want to think about ion charge, and we also want to think about the ion radius. And so here's where we can use our periodic trends to figure out which of these would have a larger radius. So I don't have a periodic table to point to you right now, but if you look on a periodic table, you'll notice that lithium is above sodium, and then over here on this side, fluoride is above bromine. And we know in general the trend is as you go down a column, the atomic radius is going to get larger. So what that means is the sodium and bromide ions, these ions are both larger. They have larger radii than lithium and fluoride do. And if we have a larger radius, let's look back at our example here. As the size of the ions increase, the distance between them increases, so the attractive force is going to decrease. So the ones with the larger radius, it's like having a larger distance between them, so they'll be less attracted. So the one with the smaller radius, smaller ionic radius, is going to be more attracted. They're going to have a larger lattice energy. Because again, remember our two variables are the force is proportional to charge over distance. So the one with a larger attractive force is going to have the larger charge or the smaller distance, which would be like your radius. Okay. Last one down here, magnesium chloride. Magnesium has a +2 charge. The chlorine ions each have a -1 charge. And over here, strontium oxide, that's a +2 -2. So the ones with the larger ion charges are going to have a greater attractive force between them. Okay. Now let's look at metallic bonding. With metallic bonding, nonmetals tend to bond covalently, but with metals, they've got a shortage of valence electrons. They might only have like, 1 or 2 valence electrons per atom, and they will kind of get together and pool their electrons and all share them in large groups of atoms that just share their electrons. All right. And what happens in metallic bonding, so you have a bunch of metal atoms that get together and they just kind of all pool together all of their valence electrons. And those electrons are not locked in any one location. They're free to move all around the solid. And that's what allows metals to conduct electricity really well, is because they have these free-flowing electrons. They can just move through the entire substance. In covalent bonding, these electrons would be locked into place. But in this metallic bonding, they're just freely moving wherever. So that's what gives metals some of their unique properties, such as conductivity. Another thing we'll talk about with metals is alloys. And alloys are mixtures involving metals. And a lot of the metals that we're familiar with on a day-to-day usage are actually not pure metals, they're alloys. An example would be 14 karat gold. That's an alloy or a mixture of gold and silver. Steel is another example of an alloy. It contains mainly iron, but with some carbon atoms in them. So alloys can actually contain some nonmetals as well, like in the case of carbon. And this is an example we call a substitutional alloy, is when the two elements you're mixing together have a similar atomic radii, and you can see this here in the visual. With an interstitial alloy, the thing that you are adding into your metal is much smaller in radius, so they'll kind of fit together differently. You see how these carbons are kind of in between the irons? That's where the name interstitial comes from. Versus substitutional, this thing you add in, like the silver, just took the place of a gold atom. Okay. And some purposes of alloys, they might increase the hardness. So like an interstitial alloy like steel will increase the hardness and durability. The corrosion prevention is another example. Stainless steel, having this chromium oxide on the surface of the metal will prevent corrosion. So this would be if you had just plain old iron and exposed it to water over time, it would rust. But stainless steel, which is an alloy, will not rust. And so that's one of the other benefits of an alloy. All right, covalent bonding is our last type of bonding. So we've gone over ionic, metallic, and then covalent. And in covalent bonding is when you combine two or more nonmetal atoms, which have high electronegativity, and they're going to get together and share electrons. And there's two types of covalent bonding. You can have molecular covalent or network covalent. Molecular covalent is the one that's much more common, that we will more often run into. And molecular covalent actually has its own set of objectives. So topics 2.5 to 2.7 all deal with molecular covalent. So we're going to get into that more later on. So we're not going to really cover that right now. But just a brief overview for right now. In molecular covalent bonding, you have a group of atoms that share electrons. That is what a molecule is a group of atoms sharing electrons. Here's an example of water molecule and how your hydrogens and oxygens are sharing some valence electrons. So we'll get into much more detail with molecular covalent later on in this unit. But for right now, we'll talk about network covalent. In network covalent bonding, you have atoms covalently bonded in this big three-dimensional network. As a result, you end up with substances that are very hard, have very high melting points. Some common examples would be diamond and quartz. The melting point of diamond is over 3,000 degrees. Here's an example of what quartz looks like. So SiO2, you might look at that formula and think, oh, it's a molecule where you have an Si bonded to two O's. But that's not actually how it works. What you have is this huge network where every silicon is bonded to 4 oxygen atoms, and every oxygen is bonded to 2 silicon atoms, and it just kind of keeps going. It's like this endless pattern here, and that's what your network covalent substances will look like. And some common examples of network covalent ones. So these are ones to know. So like memorize these common examples of network covalent compounds. So pure carbon in the form of diamond, pure silicon, pure germanium. And if you look on a periodic table, you will notice that carbon, silicon, and germanium are all in a column. They're all over there in group 4. And then quartz, so silicon dioxide, and then silicon carbide, SiC. Those are the main ones to know. And any other combination of nonmetals that is not one of these 5, you can assume that that's going to be molecular covalent. So when you put together nonmetals, you end up with covalent bonding. If it's one of these 5 examples, it's network covalent. If it's anything else, it's going to be molecular covalent. So that's the main thing to know. And then here we have an overview, again, kind of reviewing the different types of bonds we can form. So when you have 2 atoms bond together, if both atoms have really low ionization energy electronegativities, that means you're combining together 2 metals. You get metallic bonding. And you can have either a pure metal or you can have an alloy, which would be a mixture of metals. If one atom has a low ionization energy and the other one has a high electronegativity, that's ionic bonding. Your metal is going to give electrons to the nonmetals, forming positive and negative ions, which stick together due to that Coulombic attraction there. And when you have both atoms with high electronegativities, so both nonmetals, you have covalent bonding, and your nonmetals are going to share electrons with each other. They could either share electrons in small groups of atoms, that's called molecular covalent, or they could form a large three-dimensional network, and that's called network covalent. And here's another visual comparing the different types of bonding in solids. So we've got metallic, ionic, network covalent, and molecular solids. So that's an overview of the different types of bonding. Thanks for watching.